In this video, we'll cover sections 4.2, 4.3, and 4.4. What's going to happen here is that we're going to establish a lot of facts about the trig functions, what they are for basic definitions, basic properties. Going to get through a lot of basics here. The thing is, the college, the department, they basically already expect you to know this. So this section goes a little bit more quickly, and along with the idea of angles, almost all of this stuff is just so we can do the later stuff with trig. The vast bulk of your quiz that comes up on this section, of the test that's going to cover chapters 4 and 5, the vast bulk of the problems are going to come from the end of section of chapter 4, sections 4.6 and 4.7, and then chapter 5. There'll be a couple of questions that come from here. So I'm going to really try and focus this first video on just getting all these ideas. I'm not going to highlight what comes from 4.2, 4.3, 4.4, because ultimately when you're looking through the homework, you may think of something that's slightly different than what the book is trying to get you to do. And the reality is, as long as what you're doing is right, then that's fine, even if it is a slightly different strategy than what the book is trying to hope for. Okay, so let's dive in. Let's start getting some facts. The book starts with the unit circle, but I like to start with the right triangle definitions of trig functions. So I'm going to start off drawing a generic right triangle. Even when we start getting to some fancier problems, this triangle is purely going to be for reference. Sometimes triangles will be given to us, but when we have the choice, I kind of traditionally make the same setup every time. So this is my right angle, and I'm going to use the bottom corner. I'm going to label this one as my angle theta. This is going to be the angle that we focus on. So from this angle theta's perspective, there are three sides on the triangle. First one, the side that is directly across from the right angle, we formally call that the hypotenuse, and I'll just abbreviate that H when we start getting our notation set up. The side directly across from angle theta would be the opposite side, and we traditionally use an O. And then the last side, the side that connects to angle theta but is not the hypotenuse, is the adjacent side. And I'll use an A for adjacent. So one very quick thing before I get too deep here. If you put your angle theta up here, the hypotenuse is still the same, but if theta is up here, then this is the opposite, and then this is the adjacent. So it's not trivial. We have to make sure we're paying attention to what angle, where angle theta actually is. And now, the definition of the trig functions. We have three primary trig functions: sine, cosine, and tangent. But we want to get used to the abbreviations. Sine gets abbreviated SIN, and good habits with trig. The letters SIN by themselves mean nothing. We always need to have an argument inside. This is very similar to logarithms. You can't just have ln or log. It's got to be log of x, log of 3x minus 1, log of 125. Whatever the base is, you always need some argument on the inside. And the same thing with the trig functions. So here I'll use sine of theta, but maybe it's sine of x, maybe it's sine of a specific angle, 30 degrees. In general, we always need an angle, whether it's a variable, an expression, or an exact angle to go with every trig function. So again, good habits. Never just write SIN, sine of theta. Always get the angle to go with it. Similarly, cosine will be cos of theta, and tangent will be tan of theta. So really, the two primary trig functions are sine and cosine. Tangent comes up often enough that it often gets lumped in. So these are our three main trig functions, but there's also three more. There is cosecant, secant, and cotangent. That gives us 6 total trig functions. These are called the reciprocal trig functions. I'll point out why that is in just a moment. But first, just getting the abbreviations. Cosecant is CSC of theta. This one in particular, I can't tell you how many students write cosec, C-O-S-E-C. All these are abbreviated with 3 letters. So get used to the CSC, secant, SEC, secant of theta, and cotangent, COT, cotangent of theta. So now we're going to get back to the right triangle. If we have our primary 3 trig functions, there's a very nice relationship. And the one quick thing to realize, that now that all of our quizzes and tests will be take-home, you'll be able to use this and reference this as you need. But again, really think about this, everyone. If you're a calc student, you're going to have these facts memorized. It's going to come up. If you're going into any kind of physics, engineering, any of that type of science, these right triangle facts are going to come up all the time. So again, really, you should try and have this memorized. These are a basic list of facts. We could pour out page after page of facts. I'm going to try and give you the minimal list, and how if we know the minimal list, we always know enough that we could get whatever it is that we need. So, sine of theta, by definition, is the opposite value over the hypotenuse. All of these trig values will get these fractional values because this initial definition, the trig functions are equal to a ratio of sides in a right triangle. And the first ratio is this side over this side. For cosine, we'll get adjacent over hypotenuse. And then for tangent, we will get the opposite over the adjacent. For just these primary 3, there are a lot of students that know an acronym to cover this material. You've probably heard people at some point talk about the idea of Sohcahtoa. Sohcahtoa is trying to emphasize these 3 relationships, that the trig function sine is equal to the opposite over the hypotenuse, what I have right here, then the c gets me to the next function, cosine, and that is the adjacent over the hypotenuse. And then finally, tangent is equal to the opposite over the adjacent. So you'll notice when we do some problems in a little bit that if I'm going to give all the trig values, I always go in this order because that's the order they come up in the Sohcahtoa. I have to be honest though, the one catch that comes with just memorizing Sohcahtoa to try and memorize this list, I can't tell you how many people misspell the ka in the middle. Sohcahtoa, how many people accidentally get an extra O, they forget the H. It's really easy to misspell and then it loses its purpose. But again, if it's helpful for you, it is for a lot of students, that these give you the primary relationships of the primary 3 trig functions with the appropriate 2 sides for each individual trig function and the order. But now, I could also memorize definitions for these 3, but now I want to come back to the fact that they're the reciprocal trig functions. All of these 3 are 1 over one of the original 3. And again, I'm a creature of habit. I like to keep the order so I could always keep the connection. Because now when people come down here, it's not that bad for a lot of people to realize that tangent and cotangent are somehow related. But now when you come to these 2, people see the C with the cosine and the C with the cosecant, and they want to link these 2, and then the S from the sine and the S from the secant, and want to link these 2, but that is not correct. Cosecant goes with sine. Cosecant is by definition 1 over sine of theta. Secant connects with cosine. Secant is 1 over cosine theta, and then last, cotangent is 1 over tangent of theta. Next little connection, as I said in the beginning, technically sine and cosine are really the only primary 2 trig functions. We refer to these as the primary 2 because all of the others can be rewritten in terms of sine and cosine. We're already seeing that right here. Cosecant is literally 1 over sine, secant is 1 over cosine. But come back up to tangent for a moment. Tangent, again, it comes up often enough that we should keep 2 ideas. We should know the right triangle relationship, but we should also be familiar that tangent is sine over cosine. So this already, if I just knew this fact, I could deduce this fact. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. Clean up that ugly fraction, dividing fractions, you multiply by the reciprocal, you'd have O over H times H over A, H's would cancel, and you're left with O over A. So already we're starting to see I'm trying to keep a small list of facts, but again, both of these come up often enough, it's worth knowing both values. And similarly down here, cotangent is 1 over tangent. Well, tangent is sine over cosine, so cotangent is 1 over sine over cosine. But now we're also going to realize whenever you just do a simple 1 over a fraction, multiplying by the reciprocal, well, the reciprocal gets multiplied by 1, and you just get the reciprocal. So if I know, we'll use this again, once we get to some problems, you'll see me apply this. But if I know sine of theta is 2/3, well, then 1 over 2/3 would be 3/2. If cosine is radical 5 over 2, well, then secant will be 2 over radical 5. So that establishes a whole bunch of facts. And again, technically pretty much everything here comes from 4.3. But really, again, this is just going to be a bunch that we need to use just to understand. Now let me start talking about the idea of, sorry about that. Let's talk about the idea, the concept of the unit circle. That if I have a circle, it's called the unit circle because everything is 1 unit away from the origin. So let me take advantage of the easy spots. Remember this idea, if I start going at a diagonal, distance becomes a pain, but if I only go left, right, if I only go up, down, well, if I go 1 unit to the right, I'm right here, and this would have an ordered pair 1, 0. If I go directly up 1 unit, I'd be right here, and that would give me an xy of 0, 1. Directly left 1 unit, oops, sorry, right here. Directly left 1 unit would put me right here. That would be negative 1, 0. Directly down 1 unit would be 0, negative 1. Why are we drawing this? Well, again, to some people, this is where the trig functions are really originally defined. That they would draw array, look at the generic xy pair that we have that goes with this point, and the definition goes that x is equivalent to cosine of theta and y is equivalent to sine of theta. Let me write that again over on the side. This is not for all circles, it's only for a unit circle, a circle whose radius is 1, that we will get x, the x coordinate will always give me the value that goes with cosine at this specific angle theta. Again, realize the angle facts. We're using standard angles in this situation. Angle starts here. We're doing the counterclockwise for the positive angle direction. Clockwise would be a negative angle. But any of these angles, starting with the standard angle, x coordinate gives you cosine, and the y coordinate gives you sine. The book then expands that a little bit more, that y over x is the definition of tangent, but y is sine and x is cosine. That gives me this. And now let's start to realize how these ideas overlap. I can keep going. That cosecant is defined as 1 over y, and secant is 1 over x, but now we're just starting to get too repetitive. We're repeating the same facts that we already had up here. So that 1 over y is 1 over sine. 1 over x is 1 over cosine. But let's realize, let's take a quick moment. I want to leave this picture a little more clean, but let me just draw another side picture right here and point out a little fact. That if I have this setup, and there is angle theta, I could see how these facts are already starting to overlap. If I make a right triangle, and any time we make a right triangle in the xy axis, we will always do that by going to the x-axis. This would be a right triangle if I went this way, and that would be my right angle. But we'll always do that going to the x-axis. So with that setup, and that's my specific angle theta, then this is the opposite side, this is the adjacent, this is the hypotenuse, but it's a unit circle. So the hypotenuse is just a radius, so that has length 1. And now we've got a little bit more here. Instead of just calling this the opposite, let's realize whatever the height, whatever this side of the triangle is, it would be equivalent to the y value. If this is the xy pair, square root of 3 over 2 comma 1/2, well, the 1/2 would represent how far up down we went. So the y value really coincides with the opposite. And then the x value is how far left right I went. Right? If I, again, told you that this point is radical 3 comma 2 comma 1/2, I would have gone radical 3 over 2 this way and then up 1/2, and that's how I would get to this point. That's how our xy pairs work. And now apply the right triangle definitions up here. We would get sine of theta would be opposite over hypotenuse, would be y over 1, and y over 1 is just y. I'm just using a right triangle fact to establish this is a fact. Similarly, if I did cosine of theta, I would have adjacent over hypotenuse. That would give me x over 1, which is the same, the equivalent of x. So what I just did here, I'm not trying to confuse you, everybody. I'm trying to keep my facts clean. We need these facts up here. We need these facts over here. But what I'm just trying to show you very quickly is how a lot of this is overlap. That the right triangle definition verifies that x goes with cosine and y goes with sine with this specific situation. If you went in the other direction and had this as the basic definition, you use similar triangles. You'd look at bigger and smaller circles and realize triangle facts, sides for similar triangles are always in the same proportion. So we'd realize that the x over 1 here in general would go along with adjacent over hypotenuse. That the y over 1 here would be generalized opposite over hypotenuse. So again, everything we're seeing here is a lot of overlap. But what we get here is 2 more key facts. That with this picture, we've got right triangles. We have to realize that Pythagorean theorem is going to come up. Right triangles, generically we say Pythagorean theorem is a squared plus b squared equals c squared, but we just have to be very clear that the c is always the hypotenuse. So with that setup, we would have, applying Pythagorean theorem here, x squared plus y squared equals 1 squared. Squared plus squared equals this side squared, and 1 squared is just 1. But now let's translate that in terms of the trig functions. X is cosine, so x squared is cosine squared. And notice, that is traditionally where we put exponents on trig functions. If you put it here, it looks like the angle is being squared, not the trig function. So that's how we write cosine squared plus y squared is, well, y is sine, so y squared becomes sine squared, and that still equals 1. We got that from the Pythagorean theorem, so this is now known as the Pythagorean trig identity. That is just one of many trig identities, but that's the first most basic one we have to start with. There are a lot more. I could start playing the games with the definitions up here. Divide everything by cosine squared. Well, cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared is tangent squared. 1 divided by cosine squared is secant squared. That would be a whole new identity that started with this one. 1 plus tan squared equals secant squared. I can go back, divide everything by sine squared, and I get cotangent squared plus 1 equals cosecant squared. So I could keep playing a lot of games here with that, but this is the primary identity we must know, and that comes as a direct result from this setup for our trig functions. And same thing with this second to last idea. If we just look at a right triangle, if this is already 90 degrees, this angle can't even be 90 because we already mentioned all 3 angles have to add up to 180. So this covers theta in very nice acute angle situations. But can theta be bigger than that? Of course. We looked at the angle video and we talked about angles are not unique. Angles can go on forever. There can be 1,000 degrees, 1,200 degrees. We're just making loops and loops around our circle. So angles can definitely be bigger, but now this idea of the unit circle helps us understand what happens to the trig functions when we go outside of a regular triangle, when we start getting bigger and bigger angles that don't make sense in a traditional triangle. And what we realize is if we go around this circle, the x's and y's just keep repeating. The xy here is basically the same as the xy here. The y value is literally the same. The x would just have the opposite sign. If this is x is positive 1/2 on this side, this would be x is negative 1/2 on this side. Similar if I start going down here. So I keep getting the same x and y's numerically. The only thing that changes as I start going into the other quadrants are the plus or minus values that go with it. So for me, this unit circle also serves that purpose. Well, if x is cosine, anytime you're over here in quadrants 2 or 3, the x's over here would all be negative, therefore cosine is negative. And anytime I'm over here in the first or fourth quadrant, the x's over here would all be positive. They're all going to the right from the origin, so cosine would be positive in these two quadrants. Similar for sine, except now I'm going to focus on y. Anytime I'm above the origin, so anytime I'm in quadrants 1 or 2, all of these y's would be positive, so sine would be positive in these two quadrants. But anytime I'm in quadrants 3 or 4, now my y values down here would all be negative. I'd be going down from the origin, so all these would have negative y's, and then sine would be negative. And then for all the other trig values, you're thinking about how you break them down to sines and cosines. So that works for some people, but a lot of us, especially for the people who took the 121 trig class, a lot of people also learn this idea of ASTC. I'm sorry, let me do that again. ASTC. That when you use this acronym, you got to fill it in the right order, starting with quadrant 1, 2, 3, and 4. And what this is supposed to tell us, it's supposed to try and give us the hint which trig functions are positive in the respective quadrants. And what this literally tells me is, well, the A stands for all. All the trig functions are positive in the first quadrant. Over here, S stands for sine. Only sine is positive, meaning cosine and tangent would both be negative in this quadrant. Come down here, the T is short for tangent, so tangent is positive in this quadrant. Well, what if you don't have tangent? Sine or cosine would both be negative in this quadrant. And last but not least, the C stands for cosine, so cosine is positive in the fourth quadrant, but then sine and tangent, the other two, would be negative. This only considers those primary three trig functions. You still have to rely, how do I know if cosecant is positive or negative? Well, I think about sine. If I'm in the third quadrant, sine is negative, so doing 1 over sine, I'd still end up with a negative. The last fact, this has been, again, quite a bit in this video, so let me just give you the last fact. The last thing we need to know is what we refer to as a reference angle chart. We're going to focus on some very specific reference angles, oftentimes 30 degrees, 45, and 60. A lot of books focus on just these three. We can do ourselves a big, big favor if we also include 0 and 90 degrees here. So if we have this chart, I know some people have you memorize a few special triangles. If you would like, I could certainly make a quick video that'll show you why these values are what they are, but I really, again, I want to focus, keep this as brief as possible to just keep all of our facts accumulated. I'm going to make another video to go with this, and we'll just keep going back and showing how all these different ideas get used in different places. So a lot of facts to keep track of, and ultimately it's the values that we need to know. I'm going to fill in sine of theta. Oh, sorry about that. I need to leave a space for 0. So I'm going to put in my sine of theta right here and cosine of theta right here. So these are my important angle thetas. And we're going to get the values for each of these trig functions. I'm sorry I messed up this first one. I'll squeeze the value in here though. And there's a nice little technique that I'll come back to in just a moment. But for right now, let me get to the point. Let me get the values. Sine of 0 equals 0. Sine of 30 equals 1/2. Sine of 45 equals radical 2/2. Sine of 60 equals radical 3/2. And sine of 90 equals 1. Now that we get to cosine, again, even if you just took the 121 class, there are lots of other properties. As you go through, the book will talk about how some of these ideas lead to these functions being even and odd. We will get to the graphs of sine and cosine in 4.5, and we'll see a little more of that. I'll bring that stuff up then. But the book makes mention of it right now. They also talk about the idea of cofunctions and cofunction identities. So there's a lot that we could get, but the last piece that we need is just what are the values for cosine? And that idea of cofunctions is that I basically get the same values, but opposite order. Cosine of 0 is 1, cosine of 30 is radical 3/2, cosine of 45 is radical 2/2, cosine of 60 is 1/2, and cosine of 90 is 0. Same values I had here, just filled in the opposite order. I could have started here with 0, then did the 1/2, then the rad 2/2, then the rad 3/2, and then the 1. So let me just take one more moment. Here's all the facts, but let me just point out two quick things. First thing, give you the idea where those values came from, and then just show you a little shortcut to making that chart. So again, a lot of people, instead of memorizing the chart, they have you memorize these two special triangles. They start off with a square and a square. Every single side is length 1. They make a right triangle by introducing a diagonal from one extreme to the other. Now they've got a right triangle. We do a little bit of Pythagorean Theorem. This side plus this squared plus this side squared equals this side squared. We get the hypotenuse has length square root of 2. And then we'd realize that this diagonal also cut these angles in half. So this is 90, but so is this, so is this, so is this. When I cut this 90 in half, I got 45 on both sides, and same thing down here. So now, what is sine of 45? Use either one. If you use this 45, opposite over hypotenuse, do a little bit with rationalizing, and you'll get the rad 2/2. And same thing with cosine of 45. The 30 and 60 is a little bit tougher. They typically start with a regular triangle, a equilateral triangle, I should say. All sides and all angles are the same measure, same length. So I'll start with all these are length 2, and if all these angles are the same, they have to add to 180, so they'd each be 60 degrees. But now I make a right triangle by using a perpendicular bisector right here. Now I get a right angle right here. That cuts this angle in half, so I get 30 on both sides. That cuts this side in half. If the whole thing was 2, now each one is 1. Focus on the 30. Sine of 30, opposite over hypotenuse, there's the 1/2. Cosine of 30, oops, I need this side. Pythagorean Theorem, you'll get this side is the square root of 3. So cosine of 30, adjacent over hypotenuse, there's the rad 3/2. And then do similar work with 60. Sine of 60, opposite over hypotenuse, there's the rad 3/2. Cosine of 60, adjacent over hypotenuse, there's the 1/2. But let me come back to that table one more time. So I had 0, 30, 45, 60, and 90. Sine of theta, cosine theta. Some people really like this trick. instead of memorizing the values, then memorize a way to make this table so they could always find the values when they need to. You start with sine, you start with 0, everything starts divided by 2, and then in your first box in the numerator, you start with the square root of 0. With 0, you have the square root of 0 in the numerator. You go over one box, and you add 1 under the radical, square root of 1. Keep going over, you keep adding 1 under the radical. That'll give me square root of 2. That'll give me square root of 3. That will give me square root of 4. And now you just clean up the values. The square root of 0 is 0. 0 over 2 is 0. The square root of 1 is 1, so you get 1/2. These two can't be reduced. This is going to come up in our problems in a few minutes. Exact values, this is what I'm looking for. Use a calculator. A few of your newer calculators are programmed with these values, but most of them give you decimal approximates. If you're in degree mode and do sine of 45, you typically get 0.7071. And sine of 60, you typically get like 0.866. The decimals keep going, I'm just cutting them off. It's just to realize these are exact values. Calculator typically gives you decimal values. And then the last one, the square root of 4 is 2. 2 over 2 is 1. After you clean these values up, same idea we did before. Same values, just the opposite order. So let me just come back here. One last thing that some students like to do. As I mentioned in the angle video, it's perfectly fine to think in terms of degrees. And even if you have radians, just convert to degrees. But for some of you who are trying to get more accustomed to radians, trying to prepare for Calc 1, write this chart not just in degrees, get the radian measurements. Get accustomed to the common reference angles and their radian equivalents. 30, well, pi is 180. 180 divided by what gives you 30? Pi over 6. 180 divided by what gives you 45? 180 divided by 4. So 45 is pi over 4. Then 60 will be pi over 3. We actually had this one when we did our angle video. That was our pi over 2. And 0 is still 0, either way you look at it. And the final thing I'll say, you might be saying, okay, that's nice. Those are the values for sine and cosine. What about the other trig values? If you wanted to know cosecant of 30, you'll use that cosecant as 1 over sine of 30. So 1 over 1/2, and you'll get 2.